In this video, we shall look at torque exerted on a current carrying loop. We shall first look at the concept of magnetic moment, which is instrumental to the discussion of torque. We shall then look at how magnetic forces creates a rotation of current carrying loop, which in turn brings us to the discussion of torque. We will then present a few solved problems based on these concepts. Let's start with magnetic moment. First of all, we need to realize that magnetic moment is a vector quantity, and we usually represent this vector magnetic moment with the following symbol mu, like that. The magnetic moment vector is usually associated with current in a loop. For example, this diagram is a circular loop, and the current is going in following direction. Or it could be a rectangular loop, like that, where the current is going in that direction, and so on. In addition to that, this magnetic moment vector is also dependent on the surface area of this loop. So if we denote the surface area with capital A, let's say, and assuming that the area is expressed in the unit of meters squared, then the magnitude of this magnetic moment is defined in the following manner. It's a product of the electric current times the surface area of that loop. So you see that the SI unit to quantify the magnetic moment vector is quite simply amp or ampere meter squared, or quite simply a meter squared. Since this magnetic moment is a vector, we need to determine the direction of this vector mu. So how do we determine the direction of this magnetic moment? We employ the right-hand rule again. We simply grab this loop with your right-hand fingers like that, and the direction of your thumb represents the vector mu. So that is how you determine the direction of the magnetic moment vector. So these fingers represent the direction of the current. Likewise, if the direction of the current around the loop is like that, so this direction is represented by that curl of your right-hand fingers, that's current, and the direction of your right-hand thumb, which is pointing downward, represents the magnetic moment vector, like that. Now let's analyze torque exerted on a current carrying loop. Let's assume you have a rectangular loop as shown below. Now you have 4 sides to the loop: side 1, side 2, side 3, and side 4. This rectangular loop carries current I in a counterclockwise direction as represented by these blue arrows. Now let's assume the entire loop is placed in a region where the magnetic field is going to the right, as represented by these green arrows. Let's also assume that the dimensions of this rectangular loop is as such. So this length is A, and that length is B. Because there is current, and the current is placed in a magnetic field, there should be forces acting on these currents. Let's examine side 1 and side 3 first. We know from our previous video the magnetic force on current carrying conductor is given by the following expression, L cross B. L is the length vector. For side 1, the length vector is going to the left. The magnetic field is going to the right, so the angle between them is 180 degrees. So that means the magnetic force vanishes for side 1. Likewise, for side 3, the length vector is going to the right, the magnetic field is also going to the right, so the angle is 0 degrees. They are parallel to each other, and the magnetic force is also 0 on side 3. Now let's look at side 2. The force on side 2 is given by I, L cross B. The length vector is going downward and has a magnitude of B. So the length vector is in this direction, the magnetic field is in that direction. When you cross from the length vector to the magnetic field, your right hand thumb will be pointing out of the board. So the direction of the magnetic force on side 2 is coming out of the board with a magnitude of IB, capital B, where this little b is the length of that side. Now side 4. For side 4, the length vector is going up, magnetic field is going that way. So as you cross from the length vector to the magnetic field using your right hand rule, your right hand thumb will be pointing into the board. So the magnetic force on side 4 is going into the board. And the magnitude of that force is still the same as for side 2. The only difference now, it's pointing in an opposite direction. So when you have a couple of forces pointing in an opposite direction with the same magnitude, we say we have a couple. And that couple of forces should be able to rotate this particular loop in a following manner, like that, about this line. So this dotted line is the axis of rotation, and the distance is a over 2 is the distance between the sides 2 and 4 from the axis of rotation, namely this dotted line. The total torque is quite simply the torque on side 2 plus the torque on side 4. The torque on side 2 is the force on side 2, which is IB, capital B, times that perpendicular distance known as moment arm, so that is A over 2. Likewise, the torque on side 4 is the force on side 4, which we have computed, IB, capital B, times that distance, which is again A over 2, which will give you IB, capital B, A. Little b times little a is just the area of the loop, and I times the area of the loop is the magnetic moment. So magnetic moment times the magnetic field gives the magnitude of the total torque. When the loop is in this position, the direction of the magnetic moment is coming out of the board using the sign convention that we have just discussed. At a later time, as this loop rotates, let's say now the position of the loop is slightly rotated like that. Since we know the field is going that way and the magnetic moment is going that way, you can see now the angle is something else. Let's call that angle alpha. So the torque obviously changes as this loop makes its rotation. So this expression is the maximum torque for this rotation. One could summarize the torque in the following manner in terms of magnetic moment. It is given by this cross product between the magnetic moment and the magnetic field. So the magnitude of the torque is quite simply mu b sine alpha, where this alpha is the angle between the magnetic moment and the magnetic field. That is the alpha. When alpha is 90 degrees, sine 90 is 1, the magnitude of that torque is maximum. If, let's say, the loop has n turns instead of just a single turn, then the magnitude of the torque can be written in the following manner. So mu is quite simply n times I times the A, which is the surface area of the loop, B is the magnetic field, times sine alpha. Alpha is the instantaneous angle of the loop. the angle between the magnetic moment and the magnetic field, that is. Let's look at the following problem. Find the magnetic moment and magnitude of torque for the cases shown below at that instant. In all cases, the current is 3 ampere, the magnetic field has a magnitude of 0.8 Tesla, and all these loops have only one term, so capital N is 1. The angle between them is the angle between the magnetic moment and the field is 45 degrees, and the radius of this particular circular loop is 1 meter. So let's do part A first. The magnetic moment magnitude is given by the current, which is 3 ampere times the surface area of the loop. It is a circular loop, so pi times the square of the radius. Radius is 1 meter square that. So you're going to get 3 pi ampere meter squared. Now the magnitude of the torque is given by the magnetic moment that we have already computed, the magnetic field magnitude times the sine of the angle between these two vectors, alpha. So mu is 3 pi, b is 0.8 Tesla, and sine 45 is 1 over square root 2, which will give you about 5.33 Newton meter. Next, let's do part B, the rectangular loop. So the current is still 3, and the area of the loop is 2 times 3, so that is 6 meters squared, and you get 18 ampere meters squared. So now the torque is given by that mu times b times sine alpha. Mu is 18, b is 0.8 Tesla, and sine 45, because alpha is 45, is 1 over square root 2. And that's going to be 10.18 Newton meter. Note that in all these cases, there's only one term. Now, part C, the triangular loop. The magnetic moment is again given by the current, 3. The surface area is half times the sides. Sides are 1 and 2, which will give you 3m meters squared for the magnetic moment. Now the torque. The torque is given by mu times the magnetic field times sine alpha, which is 1 over square root 2. So mu is 3, magnetic field is 0.8 times 1 over square root 2, which is about 1.7 Newton meter. And that solves the problem. Problem 2. A circular coil of wire with a radius of 4 cm and 12 turns carries a current of 2 ampere. The coil is in a region where the magnetic field is 0.5 Tesla. Find the maximum torque on the coil, and in what position is the torque 1/2 as great as the maximum torque. So part A, the maximum torque. The maximum torque, as we have seen, it's given by the number of turns, current, the surface area times the magnetic field, because that happens when alpha is 90 degrees, so sine 90 is 1. Substituting all these numbers, n is 12, current is 2, the area is pi times 0.04 squared, because it's given in cm, we are converting it into meter. The magnetic field is 0.5 Tesla, and that's going to give you about 0.06 Newton meter. Part B asks, in what position is the torque 1/2 that? So 1/2 the maximum value is 0.03 about, and that happens at NIAB sine of some angle. Now we want to determine what this angle is. So substituting for n, the current, the area, magnetic field, and sine alpha, and equate that to 0.03, which is half of this, one would be able to solve for alpha. And if you solve it, you will get 30 degrees for alpha. So when alpha is 30 degrees, the torque is 1/2 as great as the maximum torque, which is 0.06. And that solves the problem. Thank you for watching.